All right, welcome back. We're gonna watch this last video of chapter 7. So far we've gone through 7.1, 7.2, and this will cover very briefly 7.3 in our textbook, where we're getting into statistical inference here. So just as a reminder, you know, from the last page, what we were pretty much visualizing there with the simulations were a couple things here, and kind of what we say when they say the bias of sample proportion is 0, it just means that there's no bias, right? As long as the experiment is set up right? I mean, like no sampling bias, measurement bias, and those other biases that were previously mentioned, the bias of the sample proportion will be 0. So what it means is that in using the statistic, this sample proportion here, and estimating P, the population proportion, it's a very good estimator, right? So it's a very good estimator, so we like that. And then also it's saying, well, what about the precision, right? We talked about the precision of our estimates, like, okay, so you mean on average we're going to hit the bullseye, right? On average we'll hit the bullseye, but plus or minus how much, right? What's the variation in our hits of the dartboard, right? And so here we're talking about standard error here. And so standard error is just a square root of the product of these. Remember, this is like the proportions or probability of success that we've seen before, the product of these two over n. And so one thing to note about standard error, or really our precision of our estimator, right? I mean, as sample size increases, right? As this sample size increases, standard error is guaranteed to decrease. So that's one very important notion here to keep track of as we move forward, okay? Because you know, we're not big on you using these formulas over and over, but more or less understanding what these are and having technology to take care of these. But really understand, you know, this standard error, this precision, we're going to become more and more precise as sample size increases, okay? So of course, all of these two things are true as long as you know, the sample must be randomly selected from population of interest, either with or without replacement. And so the population parameter is P. And then of course, the sampling without replacement, the population needs to be much larger than the sample size, at least 10 times bigger is a good rule of thumb. Okay, so just to kind of reemphasize that, and kind of important there. Yeah, so let's move on to an example. So let's put these two pieces together, and what we're going to get is the normal distribution. Okay, so this section is about the central limit theorem for sample proportion. So what the central limit theorem says is that, because in the previous slides that we saw, right, when we were looking at the sample proportion over and over and over again, right, what we saw were things like this, right? These kind of these distributions of the sample proportion. And if you see them here, right, even this one here, I mean, if remember what we did, we had a class of whatever 38, 39, and we kept sampling 10 over and over and over again, and recording the proportion of cat people there, right? And so every time we kind of got to see this distribution here, this is the distribution of the sample proportion here, right? So we took a sample of 10, recorded a number of cats, and then recorded the proportion over and over. And if you look at here, it's symmetric, right? Symmetric, kind of bell curve, unimodal. It looks like a normal distribution. And so what central limit theorem says is that, guess what? It is a normal distribution. Okay, and so and they do the theory there to back up these results. But what central limit theorem says for sample proportion, it tells us that if we take a random sample from a population, and if the sample size is large and the population size is much larger than the sample size, so that's the sampling without replacement, then the sampling distribution of the sample proportion, P hat, is approximately, drumroll please, a normal distribution with mean, whatever the population proportion is, and with standard deviation, well, in this case we call it standard error, which is P times 1 minus P over N. Okay, the product of the proportion, 1 minus proportion over N, which is your sample size. Okay, so remember, this here is like the mu, the mean parameter, that's like mu. and sigma. This represents more or less our sigma, right, which is the standard deviation. So it's kind of this number here represents the typical distance we should expect to see from a sample proportion, and the true proportion p, okay, where this true proportion happens to be the mean proportion here. So if you if any case here we don't know the value of p, the true population proportion, then we can substitute it with the sample proportion to estimate the standard error. Okay, so we could do that for the standard error there. Okay, so but a lot of times what we do is like we actually don't know this value, but what we put in there are hypothesized values. That's usually what we do for some inference. Usually we put in hypothesized values and we say, okay, well, if the true proportion were this, right, how likely is it that we observe some sample proportion of something else? And we'll see an example of that later, okay? But in all cases, if we don't know p, right, because this is from the population, right? This is a parameter. Remember, parameter population. Then we're just going to substitute in p hat, which is our statistic, which is our sample proportion, which comes from the sample. Remember, sample statistic, right? So we can put p hats over here if needed. And it's just saying, it's just saying the conditions needed there in order to make that work is that, well, the sample collected randomly and observations are independent from each other. If we look at this product here between number of trials and the sample proportion, it should be at least 10. And if we look at the number of trials times the 1 minus the proportion, that should be at least 10. Okay, so what number 2 is doing is making sure when we first introduced the binomial distribution, I said it could be skewed, right? If p is very close to 0 or p is very close to 1, the binomial distribution graph is going to be either skewed to the left or skewed to the right. And so this proportion, you know, it's pretty much tied into a binomial distribution. All it is, it's the number of heads out of 10 coin flips divided by 10, right? So we just divide this binomial by the number of trials and get a proportion. Okay, but what this is doing is just making sure that, one, our sample size is large enough to do this central limit theorem. And then 2, to make sure that, well, central limit theorem is saying, look, it's normal distribution, and normal distribution is unimodal symmetric, right? So what this is doing is making sure that it's not skewed. Okay, so that's what those are there for. And then, of course, because typically when we sample from a population, we sample without replacement. It's like, you know, I don't want to record the same person's information twice. So once I record information from one subject, I'm just going to remove them from the population, not select them again. But if so, it's just saying, look, your population size, uppercase N, should be at least 10 times the sample size. Okay, so in words, population is at least 10 times larger than the sample size. Okay, so in a very short example here, what we'll show you is that stemming from concerns over the nation's obesity epidemic, researchers investigated whether children might be as tempted by toys as by candy for Halloween treats. Okay, so what they do is they kind of randomly pick these test households in 5 Connecticut neighborhoods and offer children 2 plates. Okay, so the children walk up, one with lollipops or fruit candy, and one containing small, inexpensive Halloween toys like plastic bugs that glow in the dark. Okay, so the researchers observed selections of 283 trick-or-treaters between the ages of 3 and 14, and there's the authors and the year of the study. Okay, so in the study, they're just worried about this nation's obesity epidemic, so maybe they think that kids are more inclined to select the fruit candy than the toys, right? So this is kind of like, you know, the helper versus hinderer example, where, you know, we're assuming that the babies are more likely to select the helper than the hinderer toy, right? Or even kissing the right way, right? We think maybe they're more inclined to tilt their head to the right than to the left. But anyways, so here we observed, in this study, they observed 148 kids select candy, and the sample proportion, if you do 148 over 283, that's just 0.5230. So this 148, that's kind of like our binomial divided by n here, okay? But this is our sample proportion here, right? So from our sample of 283 kids, we found that roughly 52.3% preferred candy over the toy. So what we want to do is, well, how likely is that we observe this given that there would be no preference, right? So let's go and check this out. So we have our sample size. So these are randomly selected households. And so maybe this collection of 203, the sample was also randomly selected by us randomly selecting the households. Okay, so and then our sample size is 283, right? And then our statistic is the sample proportion, which was 148 over 283, which is 52.3%. Okay, our population here could be maybe all kids between ages 3 and 14 in the entire nation, right? And our sample size was the 283 kids that were trick-or-treating in the Connecticut neighborhoods. Okay, all right, so if we just look here as far as the parameter that we're talking about, the parameter that we're talking about here is the proportion that select candy, right? We're just saying, you know, how likely are they to select candy. And really, if we're not assuming our research question, we can say, well, you know, if there's no preference, then it's really 50-50 chance that they will select the candy, right? Because either going to select the candy or the toy, 50-50 chance, right? So here on the right, it's kind of like a histogram, a probability, well, actually it's a probability distribution function, which in this case is the sampling distribution. So what we kind of listed here is that this is like a distribution of sample proportions that we should expect to see out of 283 kids, given that there's no preference. Okay, so this is more or less the sampling distribution of the sample proportion, right? If this were true, okay, if this were the population proportion, right? So kind of in this study, like, we don't know what the population proportion is, but sometimes we could just plug in a value, right, and test it. So that's what we do here. And if you look at it, I mean, in this case, it definitely looks like a normal distribution. It's definitely unimodal, symmetric, no outliers, things like that. So it does look normal here, right? And so we back up these simulation results that we created in StatCrunch with the actual theory here. So we don't go into the theory of central limit theorem, because obviously this is not a calculus-based course, but the theory backs us up, and it says here we're assuming that as far as the sampling distribution, the sample proportion, p hat, we're saying is approximately normal distribution with center at 0.5, and standard error or standard deviation, but they call it standard error because it's of the sampling distribution, is 0.0297, right? And we're just saying, if you don't know the value of p, then you can substitute p hat to estimate the standard error. So really, I mean, we don't know the value of p, but I'm just gonna plug in a half and just say, well, how likely is it that we observe that sample proportion? Okay, so as far as condition 1, we're saying houses collected randomly and candy toy selections are independent from kid to kid. And if you were to do both of these calculations, sample size times sample proportion, that will definitely be 148, at least 10. And if you do sample times 1 minus that, we'll definitely get a value that's greater than or equal to 10. Okay, and then our population size, well, we don't know our population size, but I can assume that the number of kids in the nation ages 3 to 14 is definitely going to be 10 times larger. That's definitely going to be 10 times larger than 283, or definitely going to be larger than 2,830, right? So just saying in words, all trick-or-treaters ages 3 to 14 is at least 10 times larger than our sample size of 283, right? So all of these conditions hold, and we can verify these things. So if we need to find a probability involving our sample proportion p hat, we can do it. And just to go back here, this is from a simulation. So what I did here was I just simulated 283 out of 283 kids. I simulated the outcomes, whether they selected help or candy or toy. And so pretty much I was just flipping a coin, heads or tails, 283 times, count the number of heads or count the number of times candy was selected. And I did this over and over, maybe 10,000 times to create this distribution here. So we did it before using StatCrunch and things like that, but you can see here that the distribution of the proportion, the sample proportion, it definitely is a normal distribution. Look, centered at 0.5, right? And so that's what this is verifying for us, right? Centered about 0.5 normal distribution here. Okay, so just to wrap things up, what I want to do here, so now here's where we get to use the central limit theorem, is I want to find the probability of observing a sample proportion that is at least 0.5230. Okay, so if I were to use the z-score, well, I would do 0.5230 minus the mean, which was 0.50, divided by the standard error, which is 0.0297. And that will give me a z-score of 0.77. Right, so if I use my table here, I just have to keep track that it's a greater than or equal to probability. So whatever I find in my table, which is 0.7794, I have to subtract it from 1. And what I get here is roughly a 22.06% chance. So what I'm saying is, assuming that there's no preference in how candy versus toy selection, then what's the probability of observing a sample proportion of 0.5230 and more extreme values, right? And so the thing is this, and because what we're trying to find is that, okay, 0.5230, that is definitely greater than 50%, but is it significant, right? Is it significantly far away, right? So we compare the difference between 0.5230 and 0.50, and we say, is this difference large enough to say, maybe this is significantly far away from 0.50, right? From no preference, right? So what we compare this difference to is to the standard difference that we should expect to see between any sample proportion and the proportion of 0.50, right? Definition of standard deviation. And what we get here is 0.77. So that's saying that the sample proportion of 0.5230 is 0.77 standard deviations greater than the average proportion, which is 0.50. Okay, so what we get here is that there's roughly a 22.06% chance of observing the sample proportion in larger values, assuming that there's no preference. Okay, so in this case, it's pretty likely that we observe it. So an outcome of this amount is pretty common if this is the true proportion. Okay, so it's just kind of like for us, the true proportion of cat lovers was like, 12%, and all those sample proportions that we saw, those were likely outcomes, right? 11%, 1.5%, 15%, 20%, those were likely outcomes, assuming that, right? So we see that again here. And then of course in StatCrunch, we could just calculate this. So the mean here is 0.50. The standard deviation, or standard error in this case, because we're regarding sampling distribution, is 0.0297. And then we want to find the probability of X being greater than or equal to, so I had to switch the option here. 0.5230 is actually equal to 0.21943. So in this case, we would get 21.93% versus 22.06%. So StatCrunch is going to be more accurate, okay, just because it's not using a table, it's actually calculating the area underneath the curve for any value that you give. So, but as far as the differences here, it's still roughly, they're only off by like 0.07%. Okay, they're still very, very close to each other. Actually, less than that. So, and then here you can actually see, right? So this is kind of like those probably distribution graphs that I gave you before with the dot plots, right? And I would do that. So this is saying, okay, so the sample proportions should be centered around 0.5, right? Plus or minus what? Plus or minus what? And then what I'm doing here is I'm just doing the 68, 95, 99 rule. So in here you can kind of see which sample proportions are likely to be observed, right, and which are not. So you see here like 0.65 or 0.35, they're not even on the graph here. So if we observed like 65% of trick-or-treaters select the candy, then definitely we would doubt that it's 50% chance, right? Because something impossible happened, assuming 50% chance. Okay, but it's kind of nice here that they give you a nice shaded region here, and you can say, yeah, you know, I mean, looking at this region, it seems like a pretty likely occurrence that we observed this here, right? So what we would do is we would say, well, you know, I mean, our sample proportion, it was definitely larger than 50%. It was 52.30%, but you know, given different samples, you know, we get different numbers out. So we're just saying that, and this is one of them. And so we're just saying, okay, well, it is definitely greater than 50%, but is it enough for us to conclude that kids are more likely to select the candies, right? And then of course here, what we say, well, it's very likely that you observed that, right? I mean, this area is pretty large, right? So in this case, it wouldn't be enough to conclude that that kids are more likely to select candy, right, than the toys. Okay. For example, if you remember the helper versus hinderer example, 14 out of the 16 babies selected the helper toy. That was very convincing evidence that they recognized the helper behavior, whereas this, not so much. Okay. All right, but really the story here is the central limit theorem here, and what we're doing is we can find probabilities now. So as long as these conditions are met, right, we can find probabilities of the sample proportion. And so what it boils down to is just another type of z-score. Okay, another z-score where the formulas for the standard error are a little different, and of course the mean is in terms of a proportion. Okay. All right, and of course we could use our table, right, or we could use StatCrunch to help us calculate these probabilities. Okay, but that would be all for 7.3, and that will conclude this today.